Hi everyone and welcome to the new video. Today we're going to explore the interesting world of high voltage, and we will do it within ESP32, high voltage transformer and Python. This project is interesting for several reasons. First, it's interesting from the coding perspective. We will code the Morse code that Titanic was used. Second, it is interesting from the technical perspective. We will see how the high voltage works, a high voltage transformer and the high voltage multiplier. We will see how we can control a high current load using the ESP32. And third, this project is interesting from the historical perspective. Using the high voltage multiplier, we will see how the spark gap transmitter works, and we will be able to hear the sounds that were transmitting in the air more than 100 years ago. And now let's get into it. But before we begin, there are two important warnings. The first is kind of obvious: the high voltage can be dangerous. This board is using only 12 volts power supply, but because of the high voltage transformer and the high voltage multiplier, the output voltage can be about 10,000 volts. Obviously you shouldn't touch the wires with this voltage. Keep in mind that the capacitors can hold the charge for some time even when the board is turned off. So you must be careful, and you should discharge the high voltage multiplier first before you are doing any changes. And the second, spark gap transmitters are illegal to use in the air since 1934 because they produce a lot of electromagnetic noise. So I will be using this board without connecting the antenna output, so it will be working only on my desk. And now let's get started. First, I will give a bit of the historical context. The purpose of this project is to recreate the historical radio signals transmitted by the Titanic in 1912. More than 100 years ago. If you search on YouTube, you can find various messages that were sent by Titanic during the disaster, and they sound like this. As we can see, this video was published 9 years ago and it has more than 2 million views. But the interesting thing is that these signals are incorrect. Why? The reason is simple. Titanic was built in 1911, and at this time vacuum tube transmitters were not in use yet. So the Titanic was using a spark gap high voltage transmitter made by the Marconi company. So there were no vacuum tubes and no transistors at that time. That's why this video is incorrect, and the Morse code signal was not sounding like this. So in this video we will make a small copy of the spark gap transmitter using the ESP32, and we will program it in Python. After that, we will be able not only to listen to the signal, but also to see its radio spectrum. Obviously, it is not a poor coding tutorial, and to build the hardware project, we will need some hardware. We can generate the high voltage just by downloading the high voltage library using pip. And as a first step, I will show the components we need. As we can see, I am using a breadboard, so we don't need too much soldering. I just soldered several small wires to keep things together, and let's see what we can get here. This is obviously the ESP32, and it will be brain of our system. It will generate the signal that will go to the transistor, because the ESP32 pin cannot handle the high current, so we need a special transistor for that. This transistor is RLZ. It is specially designed to be controlled from the logical circuit, so it doesn't need a special driver. Here we have two resistors. One resistor is limiting the current and second resistor is connecting to the ground, so when there is no signal the input is not floating. This knob I will use to control the high voltage level, and I will show how we can do this. As a next part I will use a high voltage transformer, and I will show how it works. The high voltage transformer has a little amount of turns in the primary coil and a big amount of turns in the secondary coil. So for example, if we put 12 volts here, the output may be about 100 times higher, so it will be about 1000 volts. Another important part is a heatsink. And the last part of this project will be this voltage multiplier, and I will also show how it works. Capacitors are keeping the voltage and the output will be higher. As we can see on the output, this circuit is multiplied the voltage 24 times. Of course, there is some loss here, so it will be not directly 24, but it's still high. So we must be careful with that. And now let's start with coding. The same way as in my previous project, I will be using Tony IDE for Python coding. But first I will show the schematic, so we will know the pin numbers. The logic is the same that was displayed on the breadboard. Here we have the ESP32. Here we have the IRLZ transistor that works as a switch. And here we have the high voltage transformer and a 12-volt input. Practically that is it. Let's start coding. As a first step, let's define the pin numbers. And here I will be using 3 pins. The LED is on board LED that is soldered on the ESP32. The PWM output will be connected to the transistor and it will be using for generating high voltage. The potentiometer input will be used to control the voltage level, and I will show later how to do this. Now I can create the pin class and it looks like this. As a reminder, I am using MicroPython, it's not a standard Python, and this MicroPython has a special classes to control the pin or PWM or ADC. Here I can define the pin like this, and I set this pin to the output. The second important concept here is PWM. It's the pulse width modulation. The ESP32 can natively generate the high frequency signal on its pin, and here I can specify the frequency as 20 kHz, so it will be used to drive the transformer. By default, the duty cycle is 0, so the transistor is off. And when the duty cycle is 50%, it will be like a square wave, so it will be good for driving the transformer. Analog input ADC or analog to digital converter I will be used to read the knob value, so I can adjust the high voltage. And as a next step, let's add the definitions for the Morse code. As we can see, I added the dictionary for the Morse code letters, so we can specify the messages we want. And now I will add the tone on method that will play the single tone. As you can see, the logic is simple. I set the LED pin to 1. Then we have a time slip for the certain duration. And then after that we turn all off. And with this method we can generate a single tone. The next method is slightly longer, but we can see the logic is simple. We have a dictionary that I declared before. For example, the character A looks like this. There are special rules for the Morse code, like the signal for dot is shorter than the signal for dash and so on. You can pause the video and read it yourself if you want. And now as an example I can create the message that was really transmitted by Titanic. This message itself is also interesting. It's not SOS like later. The SOS code was not used at that time. I can also add some print for debugging. By the way, MicroPython doesn't have a logging class, so I can use print. And practically our coding part is ready, we can run it. For now I don't need a high voltage yet, and we can debug the output using the LED. And as we can see, it is blinking, the code works. I will also connect the oscilloscope and we will see how the pulse width modulation works. As a reminder, we created the pulse modulation on this output pin with the frequency of 20 kHz. So practically when we turn on the transmission, we set the pulse width modulation to the 50%, so we get a square wave. And after the delay, we set pulse modulation to 0, so we have no signal. Let's see it. And we can see it on the screen. Why we need it? The thing is that the transformer needs AC voltage, not DC. The current change in the primary coil causing the change in the secondary coil, and because the number of turns is much bigger, we have a higher voltage. So our high voltage transformer needs an AC current, not DC. We need a variable signal. And now our coding part is done, and I will connect the high voltage. And now I will connect the high voltage transformer to the transistor output. I also need a 12 volts power supply. You can use a standard one, just keep in mind that the current can be 2-3 amps. So the ESP32 is getting power from the USB and the high voltage part is getting power from the separate power supply. I also added the second LED at the right, so we can see that the high voltage is on, which is important because you don't want to accidentally touch 1000 volts wire. Now only the ESP32 is powered, so it is safe to connect the high voltage transformer. And now let's turn the power on. And at the first we see nothing. I need to move the wires closer. And as we can see, there is a small spark of about 1-2 millimeters. Interestingly, when the voltage is high, the air becomes conductive. That's why we can see lightning in the air. And as a rule of thumb, 1 millimeter is equal to 1 kilovolt. So practically this gap is 1–2 millimeters, so we have something between 1–2 kilovolts. As we can see, it works. But I want to see bigger sparks, so let's connect the voltage multiplier. As we can see, the voltage multiplier contains a big set of diodes and capacitors. Intuitively, the logic is simple. The IC current is changing its direction many times per second, and in the 1/2 period the capacitor is charging, but the diode is preventing this current to go back. Of course, the process is not ideal, but still we have a much higher voltage. And obviously we must be careful, because the capacitors can hold a lot of charge, it can be dangerous. We must always discharge the voltage multiplier if we want to change something in the schematic. And now I soldered the high voltage multipliers to the transformer, and as we can see, it works. We see much bigger sparks, and it's not just a continuous arc, it's a set of sparks, so it works. I will wait until the evening so we will see it in more details, and I will do some fun experiments with that. Okay, I tried to make a recording in the evening, and as we can see, the spark is much better visible. I hope now we can have a better understanding of how the Morse code sounds with the spark gap. Also, I'm not sure if it is good visible on the camera, but the smaller the gaps, the higher the spark's frequency, because the bigger the gap, the more voltage is required, and capacitors needs more time to recharge. And by the way, the transmitter on the Titanic used a bit different technology. They used the so-called rotary spark gap. It was like a wheel with the rotated contacts, so it provided a stable spark's frequency. And of course, the Titanic's transmitter was huge. I think it was about 5 kilowatts. This transmitter is maybe milliwatts only. Still, at least we can get the understanding of how it works, which is nice. And now I will return to coding, and I will show how we can easily adjust the voltage in the software. As a reminder, in MicroPython we are using pulse width modulation, and the minimum value for duty off is 0, which corresponds to no signal. It's like a flat line. And the maximum number is 512, which corresponds to 50% of the duty cycle. Practically, we can send less energy to the transformer by adjusting this duty cycle, for example, from 0 to 500. And the fix is surprisingly easy. Using the analog read, we can read the potentiometer value. As a reminder, we have a potentiometer that is connected to the power and to the ground. So its value will vary from 0 to 4000, as we can see here. But for the pulse width modulation, the maximum value is 512. So practically we need to divide the signal to 8. And just a cosmetical improvement, I'm inverting the value, so the maximum will be at the right and the minimum at the left. First, let's see how it works in the simulation. I asked Gemini AI to create an HTML app, and it's surprisingly good in that today. So now we can see how it works. When I change the potentiometer value, the duty cycle changes from 0 to 50%. This is our maximum. It corresponds to the full signal that we send to high voltage transformer. And this is the minimum, when we practically see no signal at all. So we can adjust the high voltage in the software, which is interesting. And now let's see how it works on the real board. Okay, let's do the test. I am now running the software. And now, as we can see, I can turn the knob and the values are changing. I can adjust the spark intensity from 0 to maximum. As we can see, the lower the power, the rarer the sparks, because the voltage multiplier capacitors needs more time to recharge. So as we can see, we can programmatically change the intensity of the spark, which is cool. And now let's go forward. And now, as a next step, I will explain why these transmitters are actually forbidden since 1934. And to do this, I will use my SDR Play radio receiver that can receive a wideband signals up to 8 MHz. As an output of the voltage multiplier, I connected this LC circuit that will simulate the transmitter. But as I mentioned before, these transmitters are illegal to use in the air, so I am not connecting an antenna into it. So the receiver will be placed nearby and there is no actual long-range transmission. And as we can see, the result is interesting. This spark gap transmitter generates a very wideband signal. It practically works like an RF noise generator. Alas, this SDR Play receiver is not a full-fledged spectrum analyzer, but we already can see the picture. Practically all radio spectrum is covered with noise from 0 to 8 MHz. And as an example, the Titanic used a 5 kW spare gap transmitter made by the Marconi company. 5 kW is obviously a lot of power, and as I read in the old articles, when the Titanic was transmitting, all other ships had to wait. As we can see, this transmission is very noisy. It actually fills all the electromagnetic spectrum from 0 to maybe 30 MHz or even more. But it was made before the era of vacuum tubes or transistors, and obviously when vacuum tube transmitters were invented, the spare gap transmitters became obsolete. And as mentioned before, since 1930s these transmitters are banned, so we cannot listen them in the air, and the only way to test it is on a local bench like this. And it is interesting to see how it works. And that is it for this video. Thanks for watching. I hope you learned something new. If you enjoyed this video, press like and subscribe not to miss the next one. As we can see, you can control the high voltage with Python and ESP32, and it works well. Of course, there are more efficient ways to generate high voltage, not only with one transistor as we did here. And high voltage is an interesting area to investigate. If you want to see more videos about this, write in the comments below. But of course you must be careful, and as usual, safety first. The full source code for this project is available on my Patreon page. The support helps me to buy things like this for testing. Thanks for watching and see you next time.